All right, so I'm Daniel Holladay. I'm from Los Alamos. I'm going to give a brief overview of how some projects at LANL use Kokkos, mostly from the advanced simulation and computing perspective. So let's start with a brief overview of a brief overview. We'll talk some about the past, some about the present, some about the future. Who is a Kokkos developer in here or develops for the Kokkos ecosystem? Okay. Most of the time, you're going to want to throw tomatoes at me, so get them ready. Hope you brought some from your lunchbox. Ooh, that would be fun. Red cards. Oh, Christy's a user. She will be giving green cards. The developer is going to be giving red cards. All right, I'm going to go ahead and skip through a lot of it, too, because I learned I have 15 minutes. The rest of it, I don't know how interesting you'll find it. The developers will be excited about hearing about the future and fostering Kokkos community at LANL. But first, we're going to start with way back in 2008 or so, LANL actually was an early adopter of accelerators with the Roadrunner supercomputer. It was the first accelerated computer to be at #1 on the top 500, and as simultaneously being in the top 3 on the green 500. It used the cell microprocessor that was also used in the PlayStation. So let's talk a little bit more about that. So LANL applications were able to obtain, certain ones were able to obtain high performance on the cell microprocessor. The applications tended to have a lower number of expensive kernels, such as molecular dynamics and transport, where the investment per compute kernel could be much higher if you want to think about it from that perspective. However, there was a high cost of porting to the cell due to a very complicated and complex programming environment. The codes that did port achieved really good performance. The programming environment that was complex got them, really close to the metal, as they say. But the cell-specific code that they used was generally unusable on other machines. We are at a performance portability conference here, so that seems to jive. And for the code bases, like multi-physics codes that I'll talk about later, that have large numbers of relatively inexpensive compute kernels, this kind of approach where you rewrite the entire code for every machine is just pretty infeasible. We won't actually ever know, but I propose or surmise that portability layers may have changed that calculus, but because of the experience LANL had, accelerators were not really all that quickly or continuously adopted at LANL for a long time, still really to this day. And that's a lot due to the code-based rewrites that they did do were expensive and not usable on other machines. We have a lot of large code bases that really couldn't do that. There wasn't any portability that wasn't really, or performance portability that wasn't really a thing in the late aughts. GPUs also weren't really at the time like the general purpose, monstrous compute devices they are today. There would be things like OpenCL and OpenMP target offload that would, eventually bring portability. But things like OpenCL required vendor buy-in. It was actually something Kokkos solved eventually. But Kokkos did eventually arrive. LANL has, over the decade or so that it's been open source, slowly adopted it. And it's now used pretty extensively throughout the ASC program. So I'll go through several projects here over the next few slides, a little bit about the project itself, usage of Kokkos, and some of their experiences and requests to the Kokkos team. And after that, we'll talk about the future. The first is the code I work on. It's called FLAG. It's a multi-material, multi-physics AIL code. It runs on unstructured meshes, multi-dimensional. It has a range of physics from low energy density to high energy density physics. It has a lot of complicated meshing stuff, multi-materials, pick methods, ejecta methods, 3T, MHD, good stuff. We're currently undergoing a rewrite from the existing FORTRAN to C++ and using Kokkos. We use a lot of automation to write interface and transliterate some simple constructs, which really improves our productivity. There are a lot of features that we use and we would like to see a little bit more support for. One is a memory pool would really help our performance. So I would like to see from the FLAG perspective, other projects have different perspectives, but native umpire support. What I'd really like to do, yeah, Christy's pretty excited, is to be able to do SPAC install Kokkos plus umpire, and then it sort of create an umpire memory space that was like the default. Anyway, let's see here. Then there's a few other like grab bag items with parallel scan. The auto tuning thing is going to come up several times, though. Did you have a hand raised, Damien?
What do you mean the default? You mean that you allocate the memory, you say nothing, and by magic it's using something else?
Oh, just that so you select a default memory space, or the default execution space, : memory space thing would be umpire rather than, all right, I'll take it, yellow card. Let's see here. Easy to implement and well-documented kernel tuning stuff. I've looked through some of the documentation and I get about as confused as I was before. And then we do use scatter views and offset views. Those are still located in the experimental namespace. The offset views are a lot for FORTRAN, one-base versus zero-base indexing. And then there's, I guess, some of our developers have used the tutorials and found some of them are a little out of date. All right, moving. Yes.
Do you actually need offset view, or do we just need the FORTRAN one-off view?
So I did mention that they did mention that we really only need the off by one.
We should do that and
Worry about, yeah. They said that would probably be better for performance because you could specify that at compile time. Yeah, not to get too buried in the weeds. Next code is XRage. XRage is an adaptive mesh refinement Eulerian hydrocode. The last code was Lagrangian. It's mostly used for high energy density physics, such as ICF. It has things like thermal radiative diffusion, charged particle transport, electron and ion conduction, 3T, plasma modeling, as well as laser ray tracing. So on the right, here's an example. I asked for pretty pictures from projects. So here's an example of lasers impinging on a direct drive ICF target. And then some of the Kokkos features they use managed and unmanaged views. They have a custom infrastructure, which is actually pretty impressive, for easily passing FORTRAN derived types and nested derived types to C++. They convert internal FORTRAN array representations to host or device views with a single function call. What their request is, which is a little different, and that is they would like to see views become allocator aware, and they can construct them with their own allocators. One potential use would be umpire provides an allocator, or they could use other memory pools or other allocators, really. They use parallel 4 reduced scan with range policy and MD range policy, and they also make fairly extensive use of partition space for asynchronicity. They'd really like to see this more well tested and supported and moved out of experimental. I actually think that this was brought up in the last user group meeting, but they have recently run into bugs on MI300.
Do we like the interface?
I don't like the interface. So
I think they really just want asynchronicity. So however that comes about. You want to say something more, Pete?
do you not know when you construct it? Do you not know runtime, compile time, how many you want? That you always want. Do you really need to be able to say I need?
No, we don't need a variable number. A few would probably be nice, but no requirements for n.
Yeah. All right. And then I'll just say briefly, that's an indirect drive target, lasers firing on. You can't really see it, but there's baffles on the Hall-Rom wall. They're like right here. Anyway, that was a cool picture. Next code, vector, particle, and cell. It's a kinetic, relativistic, general purpose PIC code for plasma modeling from micron scale to Earth scale. We'll actually show some of those. So, and that it can handle lots of, plasma instabilities, magnetic reconnection, things like that. Here's a visualization on the right of a short pulse laser impinging on carbon foam. This is a little bit how a PIC code works. We don't really have time to get into the details, but it solves collisionless Vlasov equation. Here's their Kokkos usage. So they were able to mostly just drop in parallel 4 for four constructs. They use views for particle and field arrays. They like the swappable memory layouts. I guess they want to make sure they're aware that they have to keep their data updated. They really like the portable atomics, and they had to make some decks Kokkos aware. And then here's some pretty pictures. This is a starfish test-like explosion in the upper atmosphere showing the plasma. That little circle at the bottom is the Earth, so that's kind of the scale of the simulation. That's a hybrid simulation, by the way. Let's see here. Here's a different one showing an explosion and the effect on the magnetic field lines that I thought looked really cool. So thanks for the VPIC folks for sending me with cool movies. Let's see here. Yes, so they have some list of things from their experiences. They talked about, I guess there was some issue with the random utilities and it not supporting float. So I don't know what that was about. They talk about in-place resizable views. I'm not actually sure how useful that would be. Maybe they want some kind of a container rather than a view. They wanted I guess they didn't, some of the documentation they were confused by, and then they said they ran into some issues with the SIMD library. They also said they're willing to help fix some of that. So that's probably maybe, with the updates coming to STUD SIMD, maybe that's a nice way we could work together on that. They also requested for more tuning of team policies. And then the last one, which I don't actually know about, which is more just like a general serialization of a view. I'm not actually sure if Kokkos COM does that, or I guess they said they thought Kokkos Resilience was working on it at one point, but they also admit it may be an infeasible feature request. But go ahead, Damien.
Can you explain briefly so does it mean they want to say this view is smaller?
Yeah, I think it sounds, I didn't actually get into detail with them, but I'm guessing they want to set like a capacity, a maximum upper bound of allocation size, and then, but that's more of a container than a view. So anyway, I don't know that it's. Yeah, that's what I would think is, they would need to set it, at somewhere at runtime before the view, before the memory is allocated. So I'm just the messenger here, so apologies. All right, next code is Pagosa. It's more of a low energy density physics, Eulerian hydro code, mostly specializing 2D and 3D. It primarily deals with HE burn. They have options for program and reactive burn. On the right is taken from their manual. That's a shape charge simulation, along with Eulerian equations they solve. They're really, really new to the Kokkos game. Like the stuff they had was, hot off the presses. So here's an example of some of the work they've done, because they're a fixed mesh. They're not like an adaptive mesh. Where did I see that? Anyway, no AMR. So they have a lot of just, perfectly nested loops that they can, do stencil operations and stuff on. So it's a pretty easy, drop-in replacement. They make use of MD range. Let's see. They also maintain float and double versions of their code. They're able to do that, so templates would make that really easy to do. So far, again, it's a very early effort, but they really like using Kokkos. Apparently the documentation, they found some issues with figuring things out. I guess they want some wisdom infused into the documentation. Maybe the Slack would be a better venue for that, but they also, I guess, are interested in the restrict memory trait, and I guess they had trouble finding good documentation on that. Okay. And they wanted more information about, I guess this is kernel launching, threads and blocks are determined. I don't know how different heuristics and whatnot are used, but that was something they wanted. I don't know, they may be having issues running into performance things with MD range potentially. Oh boy, okay. And they also requested features like runtime occupancy tuning and native memory pool support, which are pretty common among, the last project I'll talk about is transport. This is deterministic X-ray transport. They don't have pretty pictures, unfortunately, but they do have pretty equations. So they have solve a 6D plus time. It's implicit integration, discontinuous, Galerkin, finite element, unstructured meshes, and they have a diffusion preconditioner and they have a sparse iterative solver to solve that. So it's a pretty complicated thing. And rather than solving a massive matrix, they do a sweep, which basically on an unstructured grid looks like, or they convert into a task DAG, which you can see on the bottom. It's that mesh gets converted to a DAG of tasks. So one of the things they talked about, and they have worked in the past with the Kokkos team, is lightweight task parallelism. I guess they say that the task stuff they've explored has mostly been geared towards large kernels, smaller graphs. They have small kernels, large graphs. They've talked about that they would probably need some sort of kernel fusion methodology or task aggregation in order to get stuff to perform well. And then they talked about threaded small dense matrix solves, which I actually have used. So I pointed them to Kokkos kernels batched, and they were looking at that as of a few weeks ago. Yeah, and like I said, that's great. I have a lot of feature requests. It's an open source project. I can do them myself. First, I want to say, yes, it is. We do have a long list, but we are very happy to have Kokkos. There was no mandate at LANL. Many of us kind of arrived independently at it, which I think kind of shows that it's a pretty mature and usable solution for performance portability. And yeah, many of the feature requests probably sound like things for codes that are new to performance portability, and newsflash, we are. Yeah, so like I said, many of the projects arrived at Kokkos independently. Thanks to the efforts of Patrick Deal, who is at the conference. I don't know if he's in the room, but we're trying to foster some more community building at LANL so that we can try to work together, because there actually are quite a few of us working on Kokkos. We hope that one day that leads to having more resources available to contribute to the Kokkos ecosystem as well. But those are very, very early efforts. There are, though, some current ones. Richard, who I seem to think in every talk I give, has been contributing to Kokkos, particularly in the realm of SPAC. And he and Christoph, both at LANL, are part of the Kokkos build and packaging working group. And so, yeah, I really want to thank Richard and Christoph for doing that, for starting it. Hopefully Patrick and I can get some more things going. And I want to thank, as well, a bunch of folks that contributed to the content of this talk. And thank you for listening. And that's what I got.
We got a couple minutes for questions.
Thank you for nice talk, and I'm interested in the automated tool to convert FORTRAN types to Kokkos or whatever. And do you have a plan to make it publicly available, or?
I'm not 100% sure. I know where's Ben? Is Ben in here? He was talking about the possibility of making it more public. Right now, it's not. It is modularized enough that it could be. But yeah, it uses Python to basically automatically write, generate code.
So we're working on FORTRAN interoperability, and we are certainly expecting that we're gonna get some reviews and content from you guys, so that others can benefit your experience with interoperability between Kokkos and FORTRAN.
There's also the ISO FORTRAN binding.
That's one of the things that we are hoping to get.
It's part of
from you guys.
FORTRAN 2018, and it's been really helpful for providing that, to where you can pretty easily go from a FORTRAN multi-dimensional array to a view, and it passes all the necessary information. It's standardized, so that's been pretty good. Is that it, or other questions?
Any more questions? Yeah, do we have Timothy? Here. Yeah.
I have a question maybe in the meantime. In Pagosa, you were mentioning the issue with indexing, maybe the difference also between FORTRAN and...
Yeah, between 0 and 1 base, I think is what that is.
Would a library where you don't index based on numbers, but instead based on mesh elements would that be useful to you in that case?
Potentially. I mean, I think these are like fixed grids, so they probably get a lot of performance out of just being able to iterate over like integers.
The way Kokkos operates, it's not like they have a simple, they can switch to for all cells do a thing. Their data layout and their iteration patterns are very tightly coupled together for performance. So the person working on this, for instance, they want to have something when they convert from FORTRAN to C++, that if they're going to run on a CPU machine, stays with just a simple for loop and does not do a Kokkos loop for performance concerns.
Okay, thank you, Daniel.